Okay, so good morning, everybody. So today we are going to finish the introduction of the course of Malliavin calculus, okay, for Monte Carlo methods. So let me remind you what we have done during the previous session. So during the previous session, okay, we have done this part in the introduction, okay. It was just a little introduction concerning Monte Carlo methods, okay, and we have seen together, okay, the very basics of this methodology that is based, as usual, on the strong law of large number, where we have a way to control the error we do in terms of asymptotic confidence interval, okay, through the central limit theorem, okay. And we have just seen together that, okay, we have to be careful when we do this kind of methodology, because we have, of course, some advantages. The fact that this method can be done even we don't have too much regularity concerning the mapping we integrate. It's a good point. The fact that the error we do is independent of the dimension of our problem, in the sense that the speed of convergence in the central limit theorem doesn't depend on the fact that I work with a single random variable or a random vector, okay? But I have some drawbacks, okay? By the fact that the error is in fact a random variable, okay? So the notion of error is a random variable. So that's why we handle confidence interval, and keep in mind that we can only handle confidence interval at a particular level, meaning that, okay, the quantity I want to approximate will belong to my confidence interval with a probability of 95 or 99%, but not a probability of 1, okay? And we have also seen on an example that, okay, I have to be careful with this kind of methodology, because if the variance of the underlying random variable is big, I can obtain, okay, errors that are really disappointing, okay? And what I want to do today, okay, is in the very basic framework of the Black-Scholes model, okay, to show you how we can basically use this methodology to compute, okay, quantities of interest finance that will be mainly for us, okay, the price, and quantities that are relative to the hedging of European contingent claims, okay? So we are going to be in the framework of the Black-Scholes model, okay? And keep in mind that if I want to apply Monte Carlo methods, okay, I need to be able to generate IID realizations of a random variable, of a distribution. So it means that using a computer, I need to be able to generate, okay, independent realization of a particular distribution. Okay, in the Black-Scholes model, what we have? In the Black-Scholes model, okay, I have the solution of the Black-Scholes stochastic differential equation that is given by a geometric Brownian motion. So I have more or less up to constant exponential of a Gaussian distribution. So it means that Gaussian hypothesis is crucial, okay, in the Black-Scholes frameworks, okay? So that's why we are going to start the two-day session with a very basic reminder concerning how to generate distribution using a computer, and in particular, how to generate the Gaussian distribution using a computer. So from a practical point of view, in general, okay, and for the project that you will have at the end, okay, if you want to generate independent Gaussian random variables, okay, you will use a particular command of the software you are going to deal with for the project, for example, R, okay, or MATLAB, or I don't know what you want. But I just want to remind, okay, in a few words, okay, the way we do this in practice, okay, and how from Gaussian random variable we can pass easily to of the trajectory of the Brownian motion, and so trajectory of the risky asset in the Black-Scholes model. Okay. So it's what we are going to start with. So we are maybe here. Okay, we are here. Okay, so first of all, and it won't be the topic of this course, okay, I do a strong hypothesis at the beginning. Okay, at the beginning, I suppose that I am able, okay, to generate using my computer IID uniform random variables on the interval 0, 1. Okay, so it means that you are able, I suppose this, to select randomly and independently a number between 0 and 1. Okay, so we are going to start from this. So a priori, this is not an easy task. And I give you a link here where you will have one course or one session of 2 hours, okay, that is devoted to this topic, okay, in my website. So it's not the main point of this course, so that's why I won't spend time on this, okay, but if you are interested in, okay, you will see what I mean by choosing randomly a number between 0 and 1, okay, using a computer. So I suppose that, okay, I have U1, U2, U3, UN that are IID uniform on the interval 0, 1 that I am able, okay, to generate with my computer. So in general, okay, when you use the software, okay, you have some command that allow you to do this. And typically, if you use the software R, for example, you have a command that is randu, that is random uniform, okay, that will allow you to do this. Okay, so if you write randu of 1, you obtain 1 realization of a uniform on the interval 0, 1, okay, and if you do randu of, let's say, 1000, you will have 1000 independent realization of a uniform on the interval 0, 1. Okay, and what will be my first question today is, from this uniform on the interval 0, 1, how to generate independent Gaussian distribution. Okay, so it's the point I want to deal with, okay, today. So excuse me, I am not here. So I will do the job here. It's what I want to do. Okay. So we are going to see 2 or 3 methods. So they are full of methods, okay, in order to do this, okay, but I will remind the basics, okay, concerning this topic. Okay. So let's do this way. Okay. So you know that when you have a real random variable, okay, its distribution is characterized by what we call the distribution function. And we know that this distribution function has some interesting properties. Okay, it's a mapping that is, in fact, non-decreasing. Okay, it's not necessarily strictly increasing, but not decreasing. It is right continuous with left limit. The limit in plus infinity is 1. The limit in minus infinity is 0. And in fact, as all the mappings that are increasing, okay, it is possible to define what we call the generalized inverse of the distribution function. Okay, the generalized inverse I define here. It's something that you can always define for a mapping that is non-decreasing. So let's do a little picture to show you. So I want to represent here, okay, something that will look like a distribution function. So if I am a distribution function, my values are between 0 and 1. I know that my limit in minus infinity is 0, so I have something like this. Here in plus infinity, it's 1, so I have something like this. I am non-decreasing, right continuous. Okay, so I can write something like this, let's say. So I will start by being, okay, strictly increasing. Okay, and here I will suppose in this example that I will have one jump. Okay, one jump this way, for example. Why not? Okay, so you have here an example of something that can be a distribution function. So just be careful. I need to be right continuous. So I will have something like this here and something like this here. Okay. So if I take a point X here, you have here f capital X of small x, okay, the value of the distribution function, and you may have a jump here, okay, a jump that will tell you that at the point where you will have a jump, okay, the probability to take the value of this point, okay, is non-zero. So it's not here a distribution function that is related to a continuous random variable, okay. Okay, what is the way we define the generalized inverse of f of x? So if I take a u in the interval 0, 1, this way, I define, it's a definition, f x minus of u. That is what? The infimum of the x belonging to R such that the distribution function at the point small x is greater than my u here. Okay? So let's do this with my example here. So I want to find the infimum here. So I start from minus infinity. Okay, so if I am here, my distribution function is less than small u. It is less than small u, less than small u, less than small u. And in fact, I see that, okay, the point where I become greater than u is exactly this one here. This one, f x minus of u. That is the point here where we have, for my example, where we have the jump, because below we are less, and at this stage, okay, we become greater. Okay, so it is what we call the generalized inverse, and the fact that the generalized inverse is well defined, it's because, okay, we have these properties for the distribution function. Okay, so be careful. This is the generalized inverse. Okay, it's not the inverse fx minus 1, okay, as you know, when you have a mapping that is bijective. But what we can say is that when you have the distribution function that is strictly increasing and continuous, in the situation where, okay, you don't have jumps, let's say, and where we are strictly increasing, you have a mapping that is bijective. And in this situation, and only in this situation, what I have called the generalized inverse, okay, coincide with the inverse, or the the inverse of the distribution function. Okay, and in some sense, this notion of generalized inverse, as we can suppose by the name, okay, is something that will allow me to generalize the definition of the inverse, even if I am not bijective, in the case where, okay, I have something that is increasing, let's say, or non-decreasing. Okay. So what is nice on this picture is that, okay, I can see the following. I have an interesting property concerning the generalized inverse, okay, is the fact that you have the following. You have that small x is less than f x minus of u, if and only if, so that is, I have this order here, if and only if f capital X of small x is less than u. Okay, so you can see this on the picture, that small x is less than this one is equivalent to the fact that the part in green here is always less than the part in red. Okay, it's what we have here. Okay, and it just comes from this definition. Fx minus is the infimum, so where you are less than the infimum, okay, the condition is not fulfilled here. Okay, So why it's interesting to have this? But because I can say the following. If I consider U, that is a uniform on the interval 0, 1. Okay? So U is a uniform on the interval 0, 1. I can consider Fx minus of U because, okay, the generalized inverse is defined for numbers between 0 and 1 here, and U, okay, with probability 1 is in the open interval 0, 1. So I have this one. So I have from my uniform here a new random variable, fx minus of u. And if I want to find the distribution of this one, okay, so I can consider, it's a classical thing I do, you have probably already done, okay, in a course of probability. If I consider so if I consider this, okay, if I consider the probability, so that is here, in fact, what I consider the distribution function of the random variable fx minus of u at the point x. Okay, I want to compute the distribution function of this new random variable here. So what is this? So concerning what I have done here, okay, this, what I have done here, okay, excuse me. So I have this one. And so concerning this inequality here, I can say that the probability that I fulfill this is the probability that, in fact, u is less than fx of small x from this one here. Because, okay, I have this equivalent, and so I have the equality between this probability. So it comes from, okay, so if I call it this one here, it comes from this equality here. And what is this one? But I have a uniform. Here you have a number that is between 0 and 1. And you know that the distribution function of a uniform, okay, the distribution function of a uniform on 0, 1, okay, is just identity in 0, 1, okay? So if I plug here the distribution function of a uniform on 0, 1 is this one. So here 1, here 1, and you have here f of u here. Fx of small x is between 0 and 1, so I have identity, and so this term here is given simply by this one. And what I can deduce from this little computation, so it's a very basic thing here, but I can deduce from this one that fx minus of u, so this one, and x have the same distribution function, since the distribution function characterizes the distribution of a random variable, okay, they are equal in distribution. They have the same distribution. So meaning that if I want to generate from U, from a uniform the interval 0, 1 that I have supposed to be able to do, okay? If I want to generate a distribution of X, I can apply this formula. So you have here a general methodology in order to do this. So the only restriction concerning this methodology is that if you want to be able to use this one, okay, you need to know this one. Huh? If you don't know this term, you have a nice theoretical result, okay, that allow you to do absolutely nothing. Okay, so it's what I can summarize here, and it's exactly what I have written here. Okay. By the fact that if you follow the uniform on the interval 0, 1, fx minus of u has the same distribution as x, okay, and it's exactly the little picture I have done. So I repeat that when fx minus is perfectly known, okay? But then you have a way to generate using a computer the distribution of X from the distribution of U. Okay, so as an exercise to do at home, okay, you can see that if I have this, I can generate, for example, using this methodology, an exponential distribution or a Cauchy distribution. So let's focus on the exponential here, okay, because Cauchy is not that much used in finance, okay? So let's take this exponential here. So you have X that follows an exponential of parameter lambda. You are able to compute explicitly here, explicitly the distribution function of X. And if I plug it, okay, so I have something that is 0 when X is negative because I have an exponential, okay, that take values, the density is strictly positive in R plus, okay, and then you have something that takes, let's say, this form, something like this, okay, with 1 here. And where here you have 1 minus exponential minus lambda x here. So you have here the distribution function f of an exponential of parameter lambda here. Okay, so you have here, and so what I see here, I see that, so here I am constant, okay, and here I am strictly positive. So it means that we are in the situation where the generalized inverse coincide with the bijection, okay, the reciprocal of the mapping here, f minus 1, okay, and it's very easy to obtain the inverse of this mapping, okay, and that I will obtain something that is related to the logarithm, okay. I just have to invert. Let me show you. So if I take y equal to 1 minus exponential minus lambda x, I can write it as what by x equal to minus 1 over lambda, the logarithm of 1 minus y. Okay, that's why that you have fx minus, okay, on r plus, that is given by this expression. If you plug inside capital U using the previous results, you obtain an exponential of parameter lambda. So here we are in the very basic situation where, okay, it's possible to use this methodology because I know explicitly the generalized inverse of the distribution function of an exponential of parameter lambda, and the same all for a Cauchy distribution of parameter. So keep in mind that here I am interested in the Gaussian distribution. And in the case of the Gaussian distribution, unfortunately, okay, it's not possible to know explicitly the generalized inverse because even I don't know explicitly the distribution function of N01. I don't know it, okay? That's why we have tables when we do statistics, okay? We don't know explicitly. But I said that we have very interesting approximation of fx minus. So I give you an example of such approximation here, and I won't spend time on the way to obtain them. Okay, but you have here, okay, a way to approximate the distribution function of the generalized inverse of the distribution function of N01. So you have, okay, an approximation of fx minus. If I plug inside capital U, that is a uniform on the interval 0, 1, using the previous methodology, I can generate, okay, N01. And here it's exactly what I have done here. So I have generated here, so what I have represented here, you have in black the density of N01, okay, meaning that I have represented 1 over the square root of 2 pi exponential minus x squared over 2. And in red, okay, you have the empirical density function. Excuse me, I am a little bit ill. Empirical density of what? Of 10,000 independent realization of a Gaussian distribution I have obtained through the previous methodology. That is, okay, I plug fx minus of u1, fx minus of u 10,000, okay, where u1, u 10,000 are IID uniform on the interval 0. Okay, so I obtained this. So you see that it matches, okay, not that bad, okay, but with a little difference here, okay, around the mean. But whatever, okay, because in practice, it's not the methodology we are going to use. So I won't discuss it too much, but it's possible, okay, to, when I approximate fx minus, okay, for the Gaussian, okay, to obtain a n sample of a uniform, of a Gaussian from the n sample of a uniform. Okay, so I have this. So in order to introduce, in fact, the methodology we use in general in order to generate Gaussian random variables. So let me just remind, okay, I won't say nothing about this theorem because it's a theorem, you know, okay, it's what we call here. It's the change of variable theorem. Okay, you have the change of variable theorem, okay, that will tell you that if I am a situation where I have x, that is a random vector, that is a function of y, where f, okay, let's say is from r to the power d into r to the power d. If you know the density of y, okay, the density of the random vector y, if f is sufficiently regular, and by sufficiently regular, I mean that I need to be a C1 diffeomorphism in the sense that I have to be C1 bijective and my inverse has to be also C1. It's what we call a C1 diffeomorphism. Then from the density of y, I am able to deduce the density of x, okay, that will be an expression dealing with, okay, the derivatives of or the Jacobian matrix of small f. Okay, so it's the change of variable theorem. So I don't spend too much time because it's something that you have used a lot. It's in the basic course of probability. And why I introduced this result, but just because, okay, if I apply it stupidly, okay, then I am able to obtain this proposition that we called the Box-Muller methodology in order to generate Gaussian random variable in 0, 1, in fact, that tell you the following. Suppose that you start from 2 uniform on the interval 0, 1. That's something that I am supposed to be able to do with a computer. And then if I apply these two formula, so G1, that is the square root of -2 logarithm of U1 cosinus 2 pi U2, and this formula for G2, then G1 and G2 are two independent and 0, 1. I have two independent and 0, 1 from my two, okay, independent uniform on the interval 0, 1. And why I have introduced the previous result? Because I am in the situation here where the pair G1, the pair G1, G2 may be written as a mapping psi of U1, U2. Here I have two independent uniform on the interval 0, 1, meaning that I know the density of the pair U1, U2, okay, psi being a C1 diffeomorphism. Applying the previous result, I am able to deduce the density of G1, G2. So you have here the proof, okay, that is in relation with the previous theorem, okay, and I can prove using this little methodology that G1 and G2 are two independent and 0, 1, okay. So here we have two nice formulas, okay, in order to obtain very easily two independent N01 from two independent uniform on the interval 0, 1, just applying, okay, basic mappings that you know. Okay. So I have this. Okay. So just a little remark, okay, even if I don't want to spend too much time, that if I compare this methodology to the previous one, okay, a priori, you can say the following. Okay, if I use the inversion method in order to generate a N01 from a uniform on the interval 0, 1, I have used this approximation for the generalized inverse. So I use an approximation. When I see this formula, a priori, okay, I said that, okay, I have an exact formula that is not based on approximation. But in fact, it's not totally true, keep in mind, because if you want to compute explicitly, okay, with a calculator or with a computer, cosinus or a logarithm, in fact, you are going to use approximations. Okay, so you have a very, very good approximation of them. It's something that we use every time when we use a calculator, okay, but we have underlying approximation. So even if this formula seems to be very, very nice, it is, okay, but don't forget that if you want to compute it in practice, okay, you have underlying approximations, okay? So if I use this formula in order to generate my uniform from my uniform Gaussian random variable, so I can do this, and it's exactly what I have done in this picture. So what I have done in this picture, so in fact, I have used, okay, so let's write it this way. I have used, okay, pairs of uniform, so U11, U21, until U1 5000, U2 5000. So you have here, okay, where I have, okay, all of them are IID uniform on the interval 0, 1. So I have, in fact, here 10,000 independent random variable following a uniform on the interval 0, 1. Okay? Using the previous formula, I transform all these random variable into the following one, G11, G12, until G1 5000, G2 5000. Okay, and here from my previous result, I have IID and 01. And in fact, what I have represented here, I have just plot, okay, what I have plot, you have here the GI1, GI2 for I between 1 and 5000. It's what I have plotted, and you see that you have a kind of circle here, okay, coming from the fact that I have two independent centered, okay, Gaussian random variable with a variance covariance matrix in this situation that is just the identity. Okay, so I have this thing. Okay. So it was just a very basic reminder, just in order to show you that, okay, generate Gaussian is something that is not that complicated, okay, from uniform random variables, okay. I can apply the inversion method, okay, using an approximation of the generalized inverse of the distribution function, or in general, it is what we do. We can use the Box-Muller transform. That is just a little result of probability, giving to you a way to transform two independent uniform into two independent Gaussian. Okay. So now I want to use what I have done in the case of the Gaussian, okay, in order to simulate the trajectory of a Brownian motion. So let me remind very quickly what is the definition of the standard Brownian motion you have seen during the first semester. So I consider a probability space, okay, and for me, a standard Brownian motion will be what? I start from 0, I am continuous, I have independent increments, and my increments are stationary and Gaussian. More precisely, bt minus bs follows the n0 t minus s for t greater than s, okay? And the independence of the increments means that, okay, bt minus bs is independent of the, okay, filtration generated by the Brownian motion at time s. That is independent of what happened before small s. Okay. So I keep in mind the definition of the Brownian motion, and I want to generate, so maybe I will make it a little bit smaller. I want to generate, it's my 8, generate a trajectory of the Brownian motion using a computer. So generate a trajectory of the Brownian motion. So first of all, so we are going to do this, okay, so on 0 capital T, why not? So first of all, you have here, okay, a stochastic process that is defined for T belonging to a sub-interval of R that is here 0 capital T. So you have an infinite number of points in 0 capital T. With a computer, it won't be possible to generate an infinite number of points. Okay, so the first thing I have to do is to do a discretization. I don't have the choice. Okay, so I take my interval 0 capital T. Okay, so just have a look on what I have written after to be sure that I will take the same notation. Okay, I will do it here. So I consider a discretization. So I will write T0 equal to 0 and Tn that is equal to capital T. So I have a discretization with n plus 1 points. Okay. And what we are going to try to do is to represent, okay, the Brownian trajectory at these points. Okay, at these points. Because I can't do better with a computer, it's not possible for me, okay, to generate an infinite number of points. I can generate a huge number of points. So in this case, I will consider a very precise discretization with a step size that is as small as I want. In fact, I can do this as small as I want. And so my problem is to generate, in fact, BT0, BT1, BTN. Okay, so it's what I want to generate. So in a second step, what can I do? So for BT0, I don't have the choice. BT0 is equal to 0 because I have a Brownian motion that is a standard one starting from 0. So for BT0, I take 0, no problem. Okay, so it means that if I want to generate my Brownian trajectory here, but I don't have the choice for the initial point. I start from 0. Okay, then I will be interested to what happened at T1. Okay, for T1. So what I know about BT1? By BT1, I know that it follows the N0 T1. And in fact, I can write it as square root of T1, G1, where G1 follows the N01. So it means that if I want to generate BT1, I just have to generate G1, that is the N01, something that I am able to do using what I have said previously. So multiplying by the square root of T1, you will obtain this point here, and I will obtain something that is, for example, here. Okay, so you have BT0, you have BT1. Okay, what you will do in order to obtain, okay, an approximation of the Brownian motion on the interval 0 t1, but we are going, so here we generate a random vector with a number of points that may be huge, okay, and if I want to obtain a process that is a good approximation of the Brownian motion, we are going to consider a process that is with continuous trajectory, and in fact we are going to consider, okay, piecewise linear approximation, okay, obtained from this random vector. That is, I will just, okay, do this between these 2 points, okay, I use as an approximation of the Brownian motion on 0 t1 this line here. Okay, so I approximate the random vector and then I build the piecewise linear, okay, approximation that is related to this random vector. Let's continue. For B of T2, I can say exactly the same. Okay. So is it possible to do the same as I have done previously? That is, previously what I have done, I have generated G1 in order to obtain this point. So if I generate G2 here, okay, is it possible to obtain B of T2? But the answer is yes, but I have to be careful because here, be careful, G1 and G2 are not independent. They are not independent because I know that the covariance between BT1 and BT2 here is just equal to T1. So it is possible to see what is the covariance between these two random variables. Okay, it's not equal to, it is not equal to 0. So they are not independent. So it means that a priori, what I am able to do from the first step of the session here is I am able to generate independent and 0, 1. Here they are not independent. So I am not in the situation where I am okay with what I can do. But in fact, we are going to use, so this is not a good idea to write this directly here. Instead, so it's better to do the following. So let's do it in red. So better to do the following. In fact, if I want to generate B of T2, I write it this way. B of T2 minus B of T1 plus B of T1. And as always for the Brownian motion, you make appear independent increments here. Okay, you make appear independent increments. So BT2 is equal to BT2 minus BT1 plus BT1. Okay, so I have this. From the previous step, I know this one. It is known from the previous step. It is the point in blue here, BT1. So what I know for this one, but what is nice here is that what I know for this one is that this one follows the n T2 minus T1, n T2 minus T1 that is independent of BT1. So it means that if I want to do the job here, what I have to do, I have simply to do the following. I have to generate a square root of T2 minus T1, G2 plus BT1, where here G1 is independent of D2. So now, okay, instead of doing the problem directly, making appear the increment between T1 and T2 in the expression of BT2, okay, doing this, I am able to come back to the case where I have to generate a G2 here that is independent of the first Gaussian I have used. And I am able to do this using the previous methodology. So here, doing this, applying this formula, so BT1 is known, that is the blue point here, and then I obtain BT2 just adding the square root of T2 minus T1 multiplied by N01 that is independent of the first N01. So for example, I obtain something like this. Why not? We have T2 here And I can say that I obtain a thing that is here, why not? And to approximate, I put a line between these 2 points. And so on and so on. So it's exactly what I explained in details, okay, in the next slide, okay. So I want to generate the brand motion, okay, from this subdivision, and the idea is to make appear, okay, increment of the brand motion. Because I know that the brand motion has, okay, an independence property concerning increments, okay? And then the proposition I have written here is exactly what I have explained here, the way to build a Brownian motion step by step, okay, from independent N01. So the proposition you have here, the proof of this proposition is just explained in my steps here. Okay, so have a look on it. You will see that it's not complicated. So you see that at this stage here, to generate the trajectory, a trajectory of the Brownian motion using, okay, piecewise linear approximation built on a discretization of the interval 0 capital T, I have a problem here that is not more complicated than to generate independent N01, something that I am able to do. Okay, so you have this way to generate, okay, trajectory of the Brownian motion. So it's what I have done in this slide here. So here, what I have done, I have used, okay, the previous methodology in order to generate 4 trajectories, okay. So you have here 4 trajectories of BT, 40 belongings to 0,1, okay, with 1,000 points in my discretization. Okay, so you have this kind of trajectories, okay, that you can obtain. You see that, of course, I am piecewise linear. Here I start from 0, and you have the erratic behavior of the Brownian motion. Here, okay, I use only 1,000 points, okay, but it is possible to be more precise and to use more and more points, okay. So I have this. So I can drop this this one, okay, that won't be used in this course. So now, okay, let's go back to the Black and Scholl model. Okay, let's go back to the Black and Scholl model. So we'll just do a little 1 minute break, okay, to have a coffee. I come back in 1 minute. Okay, so let's come back to the course. Okay, so now we are going to work in the framework of the Black and Scholl model, okay, in order to introduce what may be the problem in using Monte Carlo methods if I want to compute with them all the quantity that are important if I want to price and to hedge in the Black and Scholl model, okay? So let me remind you basically what is the Black and Scholl model. Okay, so where I am in here. So the very basic framework of the Black and Scholl model in dimension 1 is the following. So I consider a time interval 0 capital T, where capital T will be the maturity of all the financial product we are going to consider, and typically it will be European contingent claims in this course. So not necessarily call options, but European contingent claims. Okay, the one that are characterized by their payoff, that is an F capital T measurable random variable. Okay, I suppose that I have a risk-free rate, okay, that is constant and continuously compound in this situation here. You have one risky asset that is related to this risk-free rate, okay, I suppose it to be equal to 0 at time t equal to 0 and exponential RT at time t. And I suppose for the risky asset, and I suppose a single risky asset here, and I suppose that under the historical probability P, this risky asset is the solution of the Black-Scholes stochastic differential equation, you know, okay, with an initial condition that is strictly positive, and where B is a standard Brownian motion under the historical probability P. And as you have seen in the course of stochastic calculus, okay, here I have a linear, in fact, stochastic differential equation, okay, so that has a solution that is unique. We can prove it directly in this framework, but we have also a general result that ensures the existence and the unicity of a solution to this equation. And the solution is given by the geometry Brownian motion. And what is nice in this situation is that, okay, what I see here, I see simply that ft is, let's write it as a function f of bt. So if I am able to generate trajectories of the Brownian motion, as I have done previously, and if I give you all the parameters of the model that are here, x0, mu, and sigma, you will be able, basically, applying the transform capital F to obtain, okay, an approximation of the trajectory of the risky asset, okay? So it's exactly what I have done here. Okay, so for different parameters of mu and sigma. So here it was x0 was equal to 1. For mu and sigma, you have these different values here. Okay, so you have something like this. And here, okay, I represent, okay, st for t belonging to 0, 1, that is obtained from bt, t belongs to, that is approximated as previously. Okay, I have used here, you have here 1000 points in the discretization I use in order to approximate them. So maybe just a little general comment concerning this. You know that my st is equal to x0 exponential mu minus sigma square over 2t plus sigma bt. And in particular, okay, using the properties of the moment generating function of a Gaussian random variable, if I compute the expectation of st here, I obtain x0 exponential mu t. So it means that in average here, the behavior of the risky asset is the same as the behavior of a non-risky asset, excuse me, associated with a rate that is no more r, but that is mu. Okay, I have S0 that is x0, and then the expectation of st that is obtained through this exponential. Okay, exactly the same thing as the dynamic I obtained for the non-risky asset. Keep in mind that the non-risky asset is given by, excuse me, by this expression here, multiplied by exponential RT. And here in this situation, I just multiply the initial value x0 by exponential mu t. So in average, I have this. Okay, so in the case where mu is equal to 1, it means that I obtain something. So if I plot the exponential of st here, I start from 1 at 0, it's an exponential, okay, and I obtain something like this, let's say, the same here. So it's a exponential of t here, and for mu that is negative, okay, I obtain something like this. So what can I see on these 4 examples? You see that in the case where mu is positive, okay, mu equal to 1 here, then what is the trajectory of my risky asset? But you have the tendency here, driven by the parameter mu, that is the expectation of the trajectory. And I see that I have random fluctuations around this tendency. I think that is, okay, where, okay, the fluctuations are driven by the parameter sigma, that is, okay, the parameter that control the unique source of randomness in the Black-Scholes model sigma. Okay, I have this. If I take mu equal to -1, I have the same behavior here for a sigma that is equal to 0.5. Okay, I can see here the tendency that is the exponential of -t here. And I see that I have random fluctuation around this tendency. Here, it's a little bit more complicated to see that, in fact, I have fluctuation around this tendency. It's just because, okay, my sigma is bigger here. My sigma is bigger, and for a negative mu here, okay, even if I have this underlying tendency, if the parameter sigma is too big, maybe it can be a little bit complicated to recover the tendency here. Because, okay, my random fluctuations make disappear, okay, in fact, my huge random fluctuations make disappear the underlying general tendency of the trajectory. Okay, but it was just to give you intuitions about the parameters in the Black-Scholes model, so something that I'm sure that you already know. Okay, but just keep in mind, okay, to summarize what I have said, that to generate trajectories of the geometric Brownian motion, and so to generate trajectories of the risky asset or approximations of the trajectories of the risky asset in the Black-Scholes model, it is not more complicated than to generate trajectories of the Brownian motion, and so it is not more complicated than to generate independent Gaussian random variables. Okay, so I have this. Okay, so let's continue. So what is nice in the Black-Scholes model, okay, is that I have a general formula for the price of a contingent claim in this situation. So what I mean by a contingent claim here, phi of capital T, is just a random variable that is in fact f capital T measurable. And it represents the payoff of what we can consider as, okay, a European type option that is something that I can exercise only at the end, in fact. I can exercise only at the end. Okay, so I remind you this proposition that is in the Black-Scholes model, from the Girsanov theorem, there exists a unique equivalent martingale measure, okay, that will give us, okay, the price of all the contingent claims, because the market in this situation is complete. And the completeness of the market, okay, comes from the martingale representation theorem. So we have a market that is perfect, that it is complete, that is, it is possible, okay, to obtain contingent claims as all the contingent claims as final values of self-finance portfolio with some integrability conditions, okay, regular financial portfolio that I self-finance, okay, and, okay, since I have an equivalent martingale measure, I know that the value of all these hedging portfolio are the same at any time. And what we call the price in the Black-Scholes model is just the value at time t of an arbitrary hedging portfolio. And I can prove for martingale conditions that the price at time t of a financial product represented by its payoff phi capital T, being f capital T measurable, is given by this expression. Okay, where here, when I denote by E star is just the expectation under the unique equivalent martingale measure in the Black-Scholes model. Okay, so the price is given by an expectation under Q of the, let's say, actualized payoff, conditional expectation under Q of the actualized payoff. Okay, and what is very nice in the Black-Scholes model is that I have the dynamic under the historical probability that is given by the Black-Scholes stochastic differential equation. Where B is a Brownian motion and a P. But what is very nice is that under Q, okay, I have the same kind of stochastic differential equation driven the risky asset under Q. It is this one, R ST dt plus sigma ST dWt, where W is a Brownian motion under Q. And so you see that I have the same kind of stochastic differential equation. The only thing that changed when I pass from Q to, from P to Q is the fact that the mu disappears and becomes, okay, R. Okay, this is one explanation of the fact that we'll also call this Q as a risk neutral probability. It is the probability, the unique probability, in the case of the Black-Scholes model, that make the tendency of the risky asset to be the same as the non-risky asset, in fact, because the mu here, the drift, becomes the risk-free rate, small r. And what is nice is that, okay, when I want to compute this kind of conditional expectation, I have the dynamic of the risky asset under Q that is explicitly known through this stochastic differential equation. Okay, so general framework in order to propose a good definition of the price using hedging portfolios. Okay, and once I have expressed prices using conditional expectation under the unique equivalent martingale measure, to keep in mind that I know the dynamic of my risky asset under this unique equivalent martingale measure. Okay, and you see that through this kind of expressions that a price is given by an expectation or a conditional expectation where the underlying dynamic is perfectly known. And that's why, okay, in general, it's not that complicated to use Monte Carlo methods in order to price financial products or contingent claims in the framework of the Black-Scholes model. So let me enter into more details. So where I am here. Okay. So what is nice in the Black-Scholes model, and something you know, is that you have, okay, closed form expressions for the price of call and put options. Okay, so here I have reminded the results you know, okay, from your course of stochastic calculus in the first semester. That is, okay, if for a contingent claim I take here a call option of maturity capital T and strike K, or a put option of maturity capital T and strike K, I have this Black-Scholes formula for their associated prices. Okay, so what I have written here, so I have this, yes, exactly. Okay, so the prices are given by these expressions. Okay, so I have this. So it means that in this very particular situation, computation of the prices in the case of the Black-Scholes model for the call and the put, I don't need to approximate this conditional expectation because I have nice expressions here, nice expression where, okay, here the capital N is none other than the distribution function of a N01. N is not known explicitly because I don't have a nice formula for capital N, but I have tables in order to approximate them in a very good way. Okay, so no need of extra tools in the Black-Scholes model for call and put because I have the so-called Black-Scholes formula. So I have this, okay. And I said that why the formulas for put and call options are important, but because they are easy to compute in practice, okay. And in fact, We have also in this situation what we call a benchmark, that is a way to compare, to test numerical methods. Because, okay, if I want to test a numerical method in order to approximate the price of contingent claim in the Black-Scholes model, the first step I can do is to see if my method is able to reproduce in the good way the price of the put and the call, because I have formulas for the price of the put and the call, okay? But I can also say that if I don't have closed form expression, meaning if I have a contingent claim that is no more a put or a call, okay, but what can I do? So here I have written just the price that is not a conditional expectation. Is the price, if you want, here at time t equal to 0. That's why my conditional expectation becomes an expectation, because I am at time t equal to 0. I have this expression to approximate when I am not able to compute it explicitly. And according to what I have done in the first part of the introduction, in order to approximate this expectation, I can use Monte Carlo methods, where here I have independent realization of the payoff of the contingent claim I am interested in. And I know that from the central limit theorem, I will have a 95% confidence interval for the price of such a product that will take this form here, okay, where capital sigma here will be, it's not sigma, that is the empirical variance, that is just sigma square, that will be the empirical variance of the payoff obtained, as I have explained in the first part of the introduction. So it means that, okay, in the Black-Scholes model, okay, I can use naively my Monte Carlo methods, and it's very easy to obtain approximation and related confidence interval in order to approximate the price of contingent claim in this framework. Okay, so I have this. So let's see a numerical example here. So what I have considered here. So I have considered, okay, two basic contingent claim here. So what I have done, I consider what I call a colon mean and a colon max. Okay, so in the Black-Scholes model, so here I consider capital T equal to 1. So here you have a put. Okay, a put, and you have the Black-Scholes formula for this product. Okay, and we have here a product that we call path independent, because the value of the payoff only depends on the final value of the trajectory of the risky asset. It's something that is independent of the trajectory of the risky asset. Here we are going to consider two kinds of extension of this. I consider a colon mean, that is, instead of considering a product that will give you at time capital T equal to 1, the possibility to buy the risky at the price K, I consider a product, okay, that will allow you to buy at time T equal to 1, okay, but this average against K. This average against K. Okay, it's what we call a colon mean option. Instead of having S1, I have here the average between S1 and S of 1/2. Of course, I can consider more complex average, but here it was just to illustrate the things, okay? Another product that I would consider, and here, okay, you have a product that depends on the trajectory, because it depends on the value of the risky at 1 and also at 1/2, okay? I also consider here a colon max, that is, I take the maximum between S1 and S1/2 minus K plus. So you have here a call option, a European call option, but that give you the opportunity or the right, not the obligation, to buy at capital T equal to 1, but this maximum against K. Okay. And so, okay, but in order to approximate these quantities, I can use the Monte Carlo methods, as I have explained previously, because what I have to do here, I have just to generate independent realization of this random variable, S1, S1/2, but I am able to do because I am able to generate trajectories of the risky asset from the Brownian motion. If I do this independently several times, applying the Monte Carlo methodology, I will be able to approximate such expectations. It's what I have done here. I have done the job for n equal to 10,000 or n equal to 100,000 realizations, okay? And I obtain in these situations, okay, these estimated values with these confidence interval. And of course, okay, if I increase the number of realization, I will reduce the size of my 95% confidence interval this way, okay? And I obtain something that I can consider as precise, even if, okay, keep in mind that even if in the Black-Scholes model, even if these products are very simple, I am not able, okay, to find for this product the analogous of the Black-Scholes formula for classical call options. I don't have, okay, the distribution of this random variable explicitly. I don't have distribution of this one explicitly, so I can't compute explicitly this expectation. That's why I approximate them using Monte Carlo methods. So it means that it's just two basic examples, but that in the Black-Scholes model, if I want to approximate the price of contingent claim, in general, okay, it's not that complicated to use Monte Carlo methodology in order to do this. Because, okay, the risky asset trajectory may be generated very basically from generating the trajectories of a Brownian motion. Okay, so I have this. So let's continue. Because in fact, you know that in finance, price a contingent claim, it's not the only thing we have to pay attention on. We have also in general, okay, to consider other financial quantities that are very important, in particular, the composition of hedging portfolios. And in particular, when I consider the composition of hedging portfolio, we are going to consider what we call the Greeks. Okay, so something you have already heard about, okay, but let me do some basic reminder concerning the Greeks. Okay, so here we are going to be in the following situation. So I reduce a little the slide here. So here I consider a contingent claim that has a very particular form. It's something that is path independent. It's just a function of the final value of the risky asset. So it's what we can consider as a path independent payoff. By path independent, I just mean that it only depends on the final value of the risky asset. So if I am interested in the price, so I apply the formula. Expectation in the Q of my payoff. Given FT. Okay, so if I know my course of stochastic calculus, okay, I know that the risky asset is a solution of stochastic differential equation. So it's the Markov process. And so that this conditional expectation will be obtained as a function, in fact, of the time t and of st, that is the value of the risky asset at time t. But it's very easy to recover this in the framework of the Black-Scholes model, just reminding that in order to compute this expectation, to have a nice expression of this, okay, I can write it this way. F of S capital T over ST multiplied by ST. And where? What is S capital T over ST? So why I do this? Because, okay, it's always the case when I want to make or to compute this kind of conditional expectation, I make appear a part that is FT measurable and a part that is independent of FT. In order to make appear a part that is independent of FT, I will make appear Brownian increments. So what is this one? So I am under Q. Okay, so what I am interested in is the dynamic under Q. So I have here exponential R minus sigma square over 2 capital T minus T plus sigma W capital T minus WT, where my W is the Browne motion, standard Browne motion under the equivalent martingale measure. Okay, so what I have here, so if I continue, so here I have a part that is independent of Ft. Here I have a part that is Ft measurable. And so I am able to compute the price, okay, as a function of T and of the measurable part, where Ft of X is given by what? So I pass from a conditional expectation to an expectation, exponential minus R capital T minus T, expectation under Q of what? F of S capital T over ST X. Okay, so I have this. Knowing the fact that S capital T over ST, so just let me 1 second, please. So excuse me, the baby was crying. Okay, and the mother was sleeping. So, okay. I have this, that I can express this expectation using, in fact, an integral. So f t of x may be written this way. So it's exponential minus r capital T minus t. Okay. So here I have an expectation, and here I just see that here you have something that I can write as square root of capital T minus t time n01, meaning that I can express this expectation using the density of my n01 here. And so it's an integral minus infinity plus infinity of what? Of f of, so x exponential r minus sigma square over 2 capital T minus t plus sigma square root of capital T minus t y multiplied by the density of the n01. So it's a reminder. I know that you are able to do this, but I remind it for everybody. Okay, I have this one. Okay, according to the fact that I have this. But what I can remark in fact that, and it's something that I know from my course of stochastic calculus, because when I come back to the Black-Scholes stochastic differential equation, I know that this Black-Scholes equation is homogeneous in the sense that the coefficients in the stochastic differential equation are time independent, in fact, are time independent. So I can see that here, the price function, the one that will give me the price of such a contingent claim here, that is path independent one, can be written in the following way. I can write it as the exponential of minus r capital T minus t, so the actualization factor. And this integral here can be written as an expectation, okay, of what? Of the value of the risky asset, not at time t or time capital T, but as you can see, at time capital T minus t. So I can write it as the following. the expectation under Q of F of what? Of the geometric Brownian motion here, starting at X. So I will write it this way, Sx capital T minus T. Okay. I start from X, and it's the value of the geometric Brownian motion at capital T minus T here. It's because I have here an homogeneous Markov process, in fact. Okay, so it's what I have written here. You have here the price function. You have here the price function, okay, that we are going to use later on. And keep in mind that it can be expressed this way. Where's this integral form if I want? A proposition that you have probably seen in the course of stochastic calculus, so you have seen it with me in IRFA, okay, if you have followed my course, is the fact that this mapping capital F is regular. This mapping capital F is regular, even if you don't have regularity assumption on small f. So I won't prove this proposition, but I will just show you why we have this and why it's not that surprising to have it. So maybe I will duplicate, so where I am here. I will duplicate this slide just to keep in mind, okay, what I need, that is I will erase all these things here. Yeah, and I just keep in mind this. The expression with the integral form. Okay, of course, from Lebesgue here, so you have here something that depends on t and x, okay? You have time here, time here, time here, you have small x here. So if I want to study the regularity of capital F, I have to study the regularity of an integral depending on parameters. In general, I am able to do this, okay, if I use Lebesgue type theorem, okay? But in order to use Lebesgue type theorem to do this, in general, I need the regularity of what I have inside. But it's not what I want, because when I do finance, in general, okay, when I have a contingent claim of this form, the payoff function small f is not, in general, very regular. For example, if you take a call option, you have a mapping that is not not differentiable at the strike, okay? So you have mappings that are not very regular. But I said that under very mild hypothesis, capital F is regular, even if small f is not. And by regular, I mean, okay, differentiable in the variable of interest. Why I have this? So I repeat that if I want to study the regularity of this expression here, in general, in order to use Lebesgue type theorem, I will need to have the regularity of f, because I need to have the regularity of what I have inside. But what I want to prove is a result that won't be dependent on the regularity of f. And I see that what I have here, a priori, I have something that is not that regular, and here I have something that is very, very regular. So in order to make the dependence in the parameter small x and t to be regular, but we are going to do a change of variable. If I denote by z this new variable here, what I will do, I will express my price function as this exponential here. So be careful because, okay, here z will be something from 0 to plus infinity, okay, because here you have an exponential. So y minus infinity 0, y plus infinity here, of something that will take the form of f of z, okay, and what? So I can do it explicitly, okay, so let's do if z is equal to 1, what is y? Y is equal to, okay, so the logarithm of z over x minus r minus sigma square over 2 capital T minus t over sigma the square root of capital T minus t, something that I can write as, let's say, f, let's say j of t, x, and z. So I can write it this way, 1 over the square root of 2 pi exponential, okay, minus, so g t x z square over 2 multiplied by a mapping here, that is the derivative of this one, dz. And what you see is that, and I won't enter into too much details, but what I see is that now when I do this change of variable, the dependence in the parameter, okay, in the integral is no more through small f, because here I have just the variable of integration, but through this expression that will become regular because the density of my n01 is a very regular mapping, okay? So doing this trick, I can prove that even if small f is not regular inside here, capital F will be, using this little argument of change of variable. And why it's nice for us to have, okay, a mapping capital F that is regular in the parameters, because in this way, we are going to be able to define what we call the Greeks. And what are the Greeks? But the Greeks are the derivatives of the price function, capital F, with respect to the parameters of the model. Okay, so you have several Greeks, so I won't enter into all the details here because it's something that you are supposed to know, but just let me remind, okay, the main points. So you have, for example, the delta, that is the derivative of the price function with respect to x, that is with respect to the initial condition, or excuse me, with respect to the underlying, okay, the second variable, that is the underlying. And you know that in the framework of the Black-Scholes model, this delta represent a very, very important financial quantity, that is the quantity of risky asset to put in the aging portfolio. Quantity of risky asset to put in the aging portfolio. So it's something that you have to know. Something that you have to know in order to be able to build your hedging portfolio. And in fact, it's the only quantity you need to know in order to build your hedging portfolio, because you know that by definition, your hedging portfolio will be self-financed, and that a self-financed portfolio is characterized only by the value of, by the quantity of risky asset, because the quantity of non-risky asset is a byproduct of the self-finance condition. Okay? So delta, the derivative of the price with respect to the underlying, represent a very, very important financial quantity, that is the quantity of risky asset to put in the hedging portfolio. So if I want to hedge, I need to compute this derivative explicitly. The gamma is the second derivative of the price with respect to the underlying, but it also be considered as the first derivative of the delta with respect to the underlying. So it is the derivative of the quantity of risky asset to put in hedging portfolio with respect to the underlying. And so in some sense, okay, this quantity is also very important in the Black-Scholes model because of the following. So in the Black-Scholes model, we know, it's one of the main points of the main feature of this model, is that I am able, in theory, to replicate perfectly my contingent claim. I am able to do this if my trading is done in continuous time. But in reality, and typically because in reality you have transaction cost to pay, okay, in reality, when I build an hedging portfolio, I do this, okay, discretely. I don't do a trading in continuous time, because if I do this, it will cost me a lot through the transaction cost. Okay. So if I consider a discretization of the time, okay, it means that I have discretization dates, okay. At any date, I am able to build the perfect Black-Scholes portfolio, but what happened between two dates? And in fact, what will happen between two dates will depend on the value of this gamma. If gamma is big, it means that the derivative of the delta, that is the variations of the quantity of risky asset in my hedging portfolio, will be very dependent on some variation of the risky asset itself. So it means that between two dates, I have to be very, very careful. I have to be very careful because if I have a small change in the risky asset, I may have a very big change in the composition of my hedging portfolio. And so my discretized hedging will be between two dates far from what I expect to have. Okay, so what we call the gamma, that is the sensitivity of the delta of the composition of my hedging portfolio in risky assets with respect to the underlying, will be a quantity in practice that it will be very important to know in order to handle, in some sense, the frequency of my construction of the hedging portfolio. Okay, if I have at a point and a time, okay, a big gamma, I have to be careful, and okay, the time I will wait between two positions will be small. If I have a gamma that is very small in absolute value, a little bit, because even if the underlying, okay, has big variations, the impact on the hedging, okay, will be very small. Okay, so it's also a very important quantity to know in practice. So if I continue, so in this course, it will be the two quantities on which I will focus, okay, the gamma and the delta, but okay, let me remind that you have also other definitions. You have theta, that is, okay, the dependence of the price on the time, okay, the rho, that is the dependence of the price with respect to the risk-free rate, and you have the vega. So here the vega, it's not a Greek letter, but it is also called a Greek. Okay, vega, that measure the sensitivity of the price with respect to the volatility. And for the last point, okay, keep in mind that the volatility is the only parameter, okay, that I have to estimate or calibrate in the Black-Scholes model, because, okay, my risk neutral dynamic only depend on this parameter. And the value of vega, okay, or the order of magnitude of vega in absolute value means that if I have a very small vega, okay, I can estimate roughly the volatility, because it doesn't have a big impact on the price. But if I have a big vega in absolute value, be careful, because small changes in the volatility may lead to big changes, okay, in the price function. Okay, so it's a quantity, also a very important quantity, okay, when we handle, okay, financial portfolio in order to price and to hedge in practice. Okay, so if I come back to the case of the Black-Scholes model, what is nice in the Black-Scholes model is that for call and put options, okay, all these quantities may be computed, okay, explicitly. So here in this table, what I have written, okay, I have just written the expression of the Greeks. So at time t equal to 0, okay, for call and put options, okay, you have the things, okay, for classical call and put options. For, okay, expression for call and put options of the Greeks at time t equal to 0. If you want the expressions of the Greeks at time small t and not small time t equal to 0, you just have to replace in the expressions here capital T by capital T minus small t. So it's exactly the same. What I can see in the Black-Scholes model is that, okay, so you have expression for delta, gamma, theta, rho, and vega. And you see in the Black-Scholes model that there is a link between the gamma and the vega. In fact, up to a constant, okay, these two expressions are the same, okay? Implying that when we focus on delta and gamma in the Black-Scholes model, in fact, we also take into account the vega, okay? But unfortunately, as in the case of prices, I have this nice expression for the Greeks in the Black-Scholes model, but I don't have them for more general payoff, okay? So it's exactly what I can say, okay? So in the preceding table, to obtain the values of the Greeks at time t, I just changed capital T into capital T minus t. Here, the value of the Greeks are easy to compute because I have closed form expression for call and put. And once again, if I want to test numerical methods in order to approximate the Greeks in the Black-Scholes model, this nice formula will allow me to have a benchmark in order to test these numerical methods, okay? And in this course, I will restrict myself in the computation of the delta and the gamma in financial models. Okay, so now I want to enter the main part of this introduction, that is, okay, what happens if I want, okay, in the framework of the Black-Scholes model to approximate the Greeks, simply, okay? So keep in mind what we have. If I have a contingent claim, let's say phi capital T, let's write it of this form here. The price is given by the price function, capital F, I have expressed, okay? We have seen that the delta, okay, is equal to the derivative of the price with respect to the second variable at time t, st, and the gamma, okay, is given by the second derivative of the price function with respect to the second variable, time t, st. Okay, so I will denote by delta t of x, this quantity here, and by gamma t of x, this quantity. So it's the quantity I have to compute if I want to obtain the delta and the gamma. If I plug inside ST, I will obtain, okay, what I have. That is here the quantity of risky asset to put in my hedging portfolio at time t, and here something that will give me some information concerning, okay, the time I will have to wait between two positions, okay, in order to have a good hedge. Okay, so I have derivatives. And of course, okay, if I have a derivative to approximate, okay, but I can use. So suppose that you have a mapping F, or not, let's write it J, because I don't want to put confusions. It's not this F here. So I consider a mapping J from R into R. Okay, I can consider, so if J is regular, in the sense of differentiability, I can write Taylor expansion. So I just write the Taylor expansion in this case, okay? So I suppose that I have the right to do this. So it depends on the order of regularity in terms of differentiability of J, but I have this, implying that if I use a first order approximation using this formula, okay, I can approximate from this formula. I would write it here. I can approximate G prime of X by what? By G of X plus H minus J of X over H. Okay. And if I do this, I will do an error. Okay. The error in this situation, the error I do if I use is a big O of H. Because, okay, so if you take this difference here, if you take this difference, you will obtain, okay, something that I can write as H time something that is, okay, converging toward a constant. So it's a big O of H. Okay, so it's one way to approximate the one we do in general. But I can also write, if I want to improve a little the things, I can also write the following, that G of X minus H is equal to G of X. I write the Taylor formula, okay, this way, minus H G prime of X, okay, plus H square over 2 G second of X minus H cube over 6 G third of X, and so on. Using this expression, okay, I can also approximate G prime of X here in the following way. I can do this one minus this one. If I do this one minus this one, I can approximate G prime of X by what? So this one minus this one, I obtain G of X plus H minus G of X minus H over 2H, because I have this one minus this one, so I have 2H times G prime, so I have 2H here. And if I do this one minus this one, I have simplification between these terms, okay? So the terms in G second disappear, so the terms in H square disappear. And here I do an error that is a big O of H square here. So in the case where J is very regular, okay, I have several ways to approximate a first order derivative. This classical expression here, that is the rate, in fact, okay, where an error that is a big O of H, but I can also consider, okay, here you see that there is a bias in the way I approximate, because I consider only points that are, okay, greater or smaller than small x. I don't consider these two types of points that are smaller or bigger at the same time. Okay, here it's exactly what I do. I consider points that may be greater or smaller than small x, okay, near from small x, but greater and smaller. It's not what I do here. If I do this, I improve my error. So that's why, in general, okay, we use this approximation for a derivative, okay? And this is the justification of what I have written here. That is, okay, the delta, that is the derivative of capital F, may be approximated using this formula this way. Okay, it's what we call the finite difference scheme in order to approximate a derivative by this rate. Okay. Gamma is the second derivative, and for the second derivative, I can also do the same. I will do the same if you do, in fact, what? the sum of these two expressions. If you do the sum of these two expressions, you will make disappear this first derivative, you will make disappear this one, and you will express the second derivative exactly this way. Okay, so if you subtract, you obtain this approximation for G prime. If you do the sum of these two, you obtain this approximation for the second derivative. Okay, and you will enter into more details concerning these approximations in the course concerning approximation of partial differential equation. It's exactly what we do, okay, in this situation. Okay, so I am in the following situation. So if I want to compute in practice a Greek in the Black-Scholes model, okay, I can use this approximation for the derivatives. So I have the two quantity in blue to compute. The two quantity in blue that involves what? Capital F, that is the price function given by this one. So it means that in general, I have to approximate these quantities that are not known explicitly using Monte Carlo methods. So in the case of prices in the Black-Scholes model, approximate a price can be done only using Monte Carlo methods. If I want to approximate the Greeks, I have two approximations. The one that is this one, approximate a derivative by a finite difference, and then to compute the term of the finite difference using Monte Carlo methods. So I have two sources of approximation, meaning that from a numerical point of view, this problem is in general a little bit more complicated to deal with. So it's exactly what I write here. Contrary to prices, for the Greeks, I have two factors of approximations. Okay, if I want to approximate them, one factor of approximation that comes from the finite difference game, and one coming from the Monte Carlo computation of each element of the finite difference. Okay. And here I want to show you, okay, a real dilemma I have when I want to use this kind of two steps approximations, let's say, in the framework of the Black-Scholes model. So I will need 2 slides to do this. So and maybe 3. So I have this one, and I will duplicate 3 times. Okay, so I have this. So my delta t of x may be approximating according to what I have said previously by this. It's not a K, it's an H here, huh? H to H. Okay. What is f t of x plus h? I know from what I have done previously that it is equal to what? So it is exponential minus r capital T minus t, expectation under Q, or yes, under the unique equivalent mathematical measure of what? F of S capital T minus T at the point X plus H. Yeah. That is this one. And in the same way, F T X plus H, okay, is equal to the factor of actualization, expectation under Q, F of S capital T minus T x minus h here. The minus that you have here. Of course, here I have expectations that I can approximate using Monte Carlo methods. So I can do it in this way, exponential minus r capital T minus t over capital N, sum from k equal to 1 to n of something that I can write this way, s capital T minus t, x plus h. So instead of writing k here, I will write I in order to avoid confusion between h and k, something like this, where I have here capital N independent realization of this one. Okay, I do the same for this. Okay. Okay. So I have, in fact, two Monte Carlo approximation to use in order to compute each of the two terms here in the finite different scale. Okay. So in fact, if I do a difference, I will have to compute. So I can write it this way. Let's write it explicitly. It can be written as, okay, so exponential minus r capital T minus t over 2hn, the sum from I equal to 1 to n, f of s capital T minus t x minus h I, or plus here, minus f of s capital T minus t x minus h I. Okay, so I have this. So in fact, I have a sum, I have a Monte Carlo sum to compute. In fact, that is the difference of these two. That the precision I do in the approximation of my quantity using this approximation here, it's not an equal, it's an approximation here, okay, depend on the variance of this quantity here, the variance of this quantity. If the variance is small, I will have a better approximation in the sense that my confidence interval at a particular level will have a smaller size. But I have here a difference. I have a difference, and so I will write it here. If I am interested in my quality of approximation here, I have the variance, let's say I will write it this way, of the difference, that is equal to what? The variance of the first plus the variance of the second minus 2 times the covariance between f s capital T minus t x plus h I f s capital T minus t x minus h I. I have this one. So if I want to make this variance small, if I want to make this variance small, I need to make this term as small as possible. And by as small as possible, the only way I can handle this quantity is playing with the covariance here. It means that if I want this variance to be small, I need this covariance to be big. And typically, if I want it to be big, there is a very, very bad situation for me. The very, very bad situation will be the one where the covariance is 0. Okay? Because 0 covariance, okay, will be the case where the variance will be in some sense, okay, so not maximal because I can have, okay, negative values for the covariance, but it's not a good situation. So in particular, if these two random variables are independent, okay, the covariance is 0. And so in general, my error won't be good. So that's why, and it's what I have written here, it is often better to use the same random sample for the two Monte Carlo simulations, in the sense that here and here, you have to approximate using Monte Carlo methods two quantities. These quantities are related to independent realization of, okay, the trajectory of my risky asset at time capital T minus T. I can do it, let's say, in two ways. Use two independent samples in order to approximate each quantity here, or maybe use the same sample. What I have explained to you here is to say that it's better a priori to use the same sample instead of using two independent samples to do the job. Because if I use two independent samples, okay, in order to approximate each term here, according to my little computation, the covariance will be 0 here, and so I will have a big variance here, and so a big confidence interval in the approximation of this increment by Monte Carlo methods. So when I compute, excuse me, where I am. When I compute these quantities here, okay, to approximate the delta, in general, use the same Gaussian random variable in order to compute this one and this one. Don't use two independent samples of the Gaussian, because if you do this, you will take the risk to have a big variance for the Monte Carlo estimator. And it's not what I want to have. Okay, so we take the same sample. And it's nice to have this because, okay, it is less time consuming to do this. And even, okay, it is something that will improve in general what we want. Okay. So it's my first remark here that I have to take. It's better to take, okay, the same random sample here than to consider two different ones. So let's continue with an example. Okay, a concrete example here. So here, so it's the second point here that I want to emphasize. So I will consider a particular payoff that is of this form. But for this one, I consider what we call the digital option. It is just, okay, a financial product that pay 1 if I am greater than K and 0 otherwise. Why not? Okay? 0 otherwise, 1 if I am greater than K. So it's just like to play if ST is greater than K or not, okay, in a more basic way. Okay, so if I want in this situation to approximate delta T of X, I know that delta T of X will be approximated by F T X plus H minus F T of X minus H over 2H, okay? What is F T of X plus H in this situation, by using Monte Carlo methods, I can approximate it by, okay, what? 1 over n. So exponential minus r capital T minus t. Sum from I equal to 1 to n of what? Indicator function, okay, of, I write it this way, s capital T minus t x plus h I greater than k. So something that I can write here this way. I consider independent realization, but knowing the dynamic of this one, it will be the indicator function of what? Of x plus h exponential r minus sigma square over 2 capital T minus t plus sigma the square root of capital T minus t gi greater than k, where the gi here are I, d, and 0, 1. Okay? From the fact that I am in the Black-Scholes model. So I have this. I have this this quantity here. Okay, so something that I can write here, I can write it here as the indicator function that gi is greater than what? The logarithm of k over x plus h minus r minus sigma square over 2 capital T minus t over sigma the square root of capital T minus t. I will give a name to this quantity. I will call it as d of x plus h, the notation. I have this one, okay? I can do the same for the other. But keep in mind what I have said just previously. It's better to take the same random sample in order to do Monte Carlo simulations. Don't take two independent samples. So the sample I have used here in order to generate or to approximate this quantity will be the same that I will use here because I want to have covariance. Okay, if my covariance is 0, I will increase the variance, and so I increase the size of my confidence interval. So I have exactly in the same way here, f of t x minus h that may be approximated by exponential minus r capital T minus t over n, okay, and sum from I equal to 1 to n, indicator function of gi, the same. It's important to have this in mind here. The same. This way. According to this remark here, of what? Something where what I change here, I have x minus h instead of x plus h. So something that is greater than d of x minus h. Okay? So I have this. And if I summarize what I have written here, I have written that delta of tx is approximated by what? Exponential minus r capital T minus t over 2n h. Okay, sum from I equal to 1 to n. Okay, of what? Of indicator function of gi greater than d of x plus h minus indicator function gi greater than d of x minus h, where d of z is given by the logarithm of k over z minus r minus sigma square over 2 capital T minus t over sigma, the square root of capital T minus t. So I have this. Okay. So if I want to control the error I do in this Monte Carlo approximation here, I need to have a look on the variance of what I have inside. Okay. I need to have a look on the variance of what I have inside. That is, okay, I am interested in the variance of these expressions here, the variance of this one, and we can multiply by these coefficients here. And this one. Okay, it's the variance of the term in red that I want to control if I want to control the size of my confidence interval. Okay, so I am interested here in the variance of the red part here, that is this one here, the red quantity. Okay, so just keep in mind that here, my d of z is a decreasing mapping because you have here logarithm of k over z. So this one here is just the indicator function that ji, so I am in this situation here. I have d of x plus h, and you have here d of x minus h, because you have d that is a decreasing mapping. Okay, and I consider my h to be positive here. So I have this, so I can write it this way, greater than d of x plus h less than d of x minus h. Okay, I have this according to what I have written here. So what is my variance? So if I compute it, my variance of my red term here, so I have this constant here, I can write it this way, exponential minus 2r capital T minus t over 2, 4h squared, okay? And I have the variance of this term here. So what is the variance of this term? The variance of this term is given by the expectation of the indicator function square, okay, minus the square of the indicator function, okay? Minus, so the expectation of the square of the indicator function minus the square of the expectation of the indicator function. But keep in mind that the expectation of the square of an indicator function is equal to the expectation of the indicator function because the indicator function square is equal to indicator function. So this one can be written as expectation of the indicator function factor of 1 minus the expectation of the indicator function. Something that I can compute because the expectation of an indicator function is just, okay, a probability. It's the probability that a Gaussian is between x minus h and x plus h. So it's something that I can express as n of d x minus h minus n d of x plus h, this one. So this term here is equal to this one, okay? 1 minus, I can write it this way, n of d x minus h minus n d x plus h, where capital N is, as usual, distribution function of my n01. Distribution function of my n01, okay? So I have this. Okay. So what happened for these quantities here? The first thing I can say is that this one converges toward 1 when h goes to 0, because here this difference goes to 0 here. So 1 minus this difference goes to 1. What happened for this one? This one, okay, according to what I have said previously, okay, so keep in mind what I have written here. So it's not here, excuse me. So I have this. A derivative may be approximated this way. Okay, a derivative may be approximated this way. So using this formula applied to my problem here, what I have here, I obtain minus, so this one is equivalent when h goes to 0 to minus 2h multiplied by the derivative of this one at x, that is n prime dx d prime of x. Okay, so I have this one. So just to remark, here it's a variance. So it's something that is positive. Okay, so why it is positive? So here I have something that is always greater than 0, no problem. And here I have a minus here. But keep in mind that you have a minus, but here d is a decreasing mapping. It implies that its derivative is negative. So I have negative multiplied by negative. Here you have the derivative of the distribution function of n01. So you have positive, negative, negative. So the product is positive. So no problem with the fact that I have a variance. But at the end, if I conclude my computation, what can I say about the variance of what I am interested in? This variance is equivalent to what? So I have this term multiplied by this one that is equivalent when h goes to 0 to what? To something that is a constant over h. A constant over h. And in fact, but it is a big problem to have this. Why it is a big problem? It is a big problem because keep in mind that when I approximate my delta in the two-step way, that is first using finite difference and then compute each term of the finite difference using Monte Carlo methods, I have two sources of approximation. I see that if I want to control the error in the good way, okay, I need to control this variance and I want it to be small. So I want this variance small if I want to have this Monte Carlo error term to be small. If I want to control the error from the finite difference, of course, I need to take a small h. Because if I take a small h, okay, my Taylor approximation argument will be valid. So you are in a situation where in order to make this one small, you have to take h small. To make this one small, you need to have the variance small, but the variance is equivalent when h goes to 0 to k over h. That is something that is increasing in h. So here, when h increase, you decrease the precision of your approximation here. I repeat, when h decrease towards 0, you increase your precision here, but here you decrease your precision and conversely. So you have a big dilemma because you are in a situation where when h is too big, the first part of the error increase. If you take h too small, according to what I have computed here, h too small means a big variance, so a bad Monte Carlo approximation. Okay, so we are in a situation really where if I want to approximate naively delta by the finite approximation scheme, okay, a finite difference scheme, but the two approximation I do are in some sense in contradiction if I want to control my error. To make one increase will make the other one decrease, and conversely, okay? So it means that contrary to what happened for prices, if I apply, okay, finite difference to Greeks, or at the very least for the delta, as I have explained here, okay, I may have some problems, okay, some new problems that are not problems I have, okay, when I approximate prices in the Black-Scholes model, okay. So what will be our ID? So I have done the job here, okay. So just to say what I can say here, okay, I will drop this this one, okay. So just keep in mind that, okay, my approximation, okay, scheme for the delta or for all the Greeks, okay, give rise to a dilemma, okay. Make this one small will make this one big, okay, as I have seen in my example concerning the digital option, okay. And of course, a remark that I can do, that is a remark that is relative to the next slide, that is here, the best or the more regular capital F is in the initial condition, the more precise will be my approximation here. Okay, so if I have a price function that is, okay, very regular in H, okay, my approximation will be better. So it's just what can you see here, okay, on two examples where I see that I study the dependence of my payoff function in the initial condition. I do this for what I have studied previously, that was my digital option, my binary option, and for a call option, okay, and I see that if I control the quadratic, okay, the quadratic, okay, difference between, okay, the payoff at X and the payoff at X plus H, okay, I can control it, okay, this way with the computation that is exactly for this case, the one I have done previously, and here a very basic one using Cauchy-Schwarz inequality here, or convex inequality, Jensen inequality. And you see that here, okay, I will have something that is more regular for the call and less regular for the binary option, typically because in this case I have a jump, and in this case I have a continuous payoff. Okay, so, but I will come back on this point later on. Okay, so you can drop in a first approximation this slide here, but just take into account that if I want to approximate the Greeks by delta, by finite difference scheme, the more capital F is regular in the initial condition, okay, the more efficient will be my methodology. But what I want you to keep in mind at this stage is that, okay, finite difference for Greeks in the Black-Scholes model lead in general to some numerical problems because I have finite difference versus Monte Carlo approximations to deal with, okay? And in fact, in the framework of the Black-Scholes model, we are going to see some way in order to overcome this problem. And what is nice, okay, is that for the Black-Scholes model, I will be able to drop this problem, okay, in a very nice way and a very easy way without needing to use difficult mathematical tools. So just let me know what time is it, okay, to see if I have time to do. Yeah, I will continue. I am not sure that I will have to finish the video this morning, but let's continue this and I will finish when I will finish later if I need. Okay, so integration by part for Greeks. So the idea is very simple. What I want to do is the following. In Black-Scholes, or in fact in classical financial model, price is an expectation up to constant under the equivalent martingale measure, but it's an expectation. Okay. Greeks, it's derivative of price. Derivative of price. Okay. So as I have explained, here I can use Monte Carlo methods to approximate if I am not able to have a closed form expression. Here, it's finite difference plus Monte Carlo. One source of approximation for the price, two sources of approximation for the Greeks with, as I have shown you in the previous example, with maybe some, okay, very bad situation concerning the control of these two types of error, because in general, okay, make this one small, we make this one big, okay? So the idea is very simple. I want to pass from this situation to the previous one. That is, instead of having the derivative of a price that impose me to use these two types of approximation, I want to come back to this case. And the idea is to be able, to try to be able to write, okay, the Greeks, that is the delta, the gamma, or the vega, in the following way. The expectation of the payoff, so if you remove this one, okay, the expectation of the actualized payoff is the price, okay, but it's not what I am interested in, but in fact, we are going to express the Greeks as the expectation of the payoff multiplied by another random variable, And if I do this, the interest of such a situation will be that I will express the Greeks as an expectation. To approximate this approximation, it will be sufficient for me to use methods. I won't need to use finite difference anymore in this situation. Okay? So the idea, okay, is to write the Greeks this way. What we want also is that my weight here, I want it to be independent for a large family of payoff. Typically, in the example we are going to see just after, the family of payoff we are going to see here is something of the form, okay, f of S capital T. And in fact, the weight we are going to obtain here will be the same for all these payoff independently of f. That is here, independent of f. Okay? So I want weights here that are just what I call the weight is just a random variable. If the weight is equal to 1, I recover the price. If the weight is not, I need to find the weight in order to make this equality true. And what is more, once I will have this equality, the idea will be to approximate my expectation by Monte Carlo methods. Okay, so in order to approximate this Greek by Monte Carlo methods, I will need to approximate this expectation by the strong law of large number result, okay? And if I want an error that is as small as possible, I need to obtain inside here some random variable with a variance that is minimal, because if I have a variance that is minimal for what I have inside here, I see that the size of the confidence interval will be minimal, and so the error I will do using the approximation of the error coming from the central limit theorem. So I am waiting for a weight. I am looking for a weight here, independent of the payoff f, and such that the variance of this product is minimal, because it may exist several weights here, and I want the one that is minimal. Okay, it's what I want to. Okay, so let's do. In the Black-Scholes model, I have these very nice results that give you exactly what I want. That is, okay, the following. So let me comment, and I will explain to you, okay, the proof of this one in a few words, because it's a very basic result here. Or not that basic, but the fact is I use, in order to prove it, very basic arguments. Okay, so you know that the price, so in this situation, okay, I am my contingent claim given by this expression here. I know that the price is given by exponential minus R capital T minus T, okay? Expectations under Q of the payoff, okay? I have this one, and we have seen together that the price can be written as f of t minus t, where f t of x is given simply by exponential minus r capital T minus t, the expectation under p star of what? Of f of x, not of x, I can write it this way, excuse me, f of s capital T minus t x. So the price function, as I have explained previously, is given by this one. Okay, so what is the meaning of this proposition? You see that the meaning of this proposition is that the delta and the gamma in this situation and in the Black-Scholes model, okay, may be obtained this way. What I have done from this one to this one, you see that you have just multiplied inside the price here. You have multiplied by this random variable here in the case of the delta. So just you have added here this term, or in the case of the gamma, this one that is a little bit more complicated, but that is this one. So you express exactly the delta or gamma here are expressed in the following way. I have expressed them using this proposition as, in fact, what? So expressed as expectation under P star of f of s capital T minus t small x, okay, multiplied by the weight that I denote by pi, okay, that is equal, so I can write the exponential here if I want. Problem with this, okay, with a pi here that is given by this expression in the case of the delta and by this expression in the case of the gamma, okay? So it means that I am able, okay, to have an expression of the delta and the gamma without using a derivative, okay, just writing it as the expectation under an expectation under the equivalent martingale measure of something that looks like the price just multiplied inside by a random variable that we are going to obtain just after. The way to obtain will be, I will explain to you in one second. Okay, so it's exactly what I want to do. That is to remove the derivative part, okay, in the expression of delta and gamma in order not to use the finite difference scale, okay, in this situation. Okay, so I have this. So maybe let me show you how to prove this proposition at the very least in the case of the delta. So it's the objective of the next slide, and I will explain to you how to obtain the proof in this situation. So I will explain. You have all the things here. Okay, so keep in mind that my price function is equal to what? Okay, so I repeat, exponential minus r capital T minus t, the expectation under Q of f of s capital T minus t small x here. Okay, so something that I can express as an integral because I am in the framework of the Black-Scholes model. So an integral, that is the integral between minus infinity plus infinity f of x exponential r minus sigma square over 2 capital T minus T, okay, plus sigma the square root of capital T minus Ty multiplied just by the density of N01. Okay, so the delta is by definition the derivative of the price function. Okay. And I want to handle this quantity to prove that I have the expression that I want in the proposition. So if I consider the derivative of the price here that I add here, so if I consider the derivative of the price with respect to x, I have the derivative of this integral, okay, that I have to handle. So the idea is to invert between them, okay? But in order to invert, it's the type theorem that will allow me to use this, okay? I need to suppose that what I have inside is regular. So what we are going to do is to do this. So I will do the proof in 2 steps, okay? So first step, this one. I suppose that f is very regular. So step 1, f regular. And for me, regular will mean C1 with compact support. C1 with compact support. Step 2, approximation. Okay, you approximate your f by mappings that are regular in this sense, okay, and you can pass to the limit without problem. So here, what I will do is the step 1 to show you that it works. To pass from step 1 to step 2, you just have to use, okay, approximation argument as it is written here. Okay, so if I suppose that f is very regular, that is the step 1 of my reasoning here. I can invert between the derivative and the integral, and it's exactly what I obtain here. I invert the derivative. So when, I write it this way, when f regular, you can invert the derivative and the integral using Lebesgue type theorem. Okay? Okay, so I have this. I have the right to invert using Lebesgue type theorem. And the idea is that, okay, we are going to do an integration by part. But be careful, because here I compute the derivative with respect to x, and here my variable of integration is y. So a priori, it's not what I do when I do an integration by part. But if you define by j this mapping here, you see that the derivative of j with respect to x, the derivative of this mapping here with respect to x may be expressed as a mapping multiplied by the derivative of j with respect to y. It's very easy to obtain. What you do, compute the derivative of this one with respect to x, compute the derivative of this one with respect to y, and you will see that we have this relation between the two derivatives. And what is nice if you do this is that you can replace using this derivative here by, okay, 1 over x sigma the square root of capital T minus T multiplied by the derivative of j with respect to y. And now, okay, remove the derivative with respect to x and change it into a derivative with respect to y. And now you can apply an integration by part. Okay, because you will have u prime v, okay, and you apply the integration by part formula. So if you apply the classical integration by part formula in this expression here, so you have the term exponential minus r capital T minus t multiplied by this one that is here, and then you have the integral of the multiplied by this mapping, okay? So in general, you have 2 terms in an integration by part, okay? You have the part that is, okay, so keep in mind that the integration by part formula is this one, u prime v, that is equal to u v minus integral of u v prime. Okay, it's this one that we have, integration by part formula. So here I have the integral of u prime v. Okay, I will have minus the integral of u v prime with v prime, that is just the derivative of this one. That's why I obtain this quantity, minus the derivative of this one, give me this expression here. And I don't have this extra term in this situation because, but typically because in plus and minus infinity, this mapping, okay, the limit of this mapping are 0 in plus and minus infinity. So you don't have this extra term in the integration by part. Okay, so I repeat. I express delta this way, inverting the derivative and the integral. I want to obtain an integration by part in order to remove the differentiation with respect to this mapping here. I just remarked that the derivative with respect to x of this mapping here may be expressed as a mapping multiplied by its derivative with respect to y. I plug inside exactly what I have done here. And now I am able to do an integration by part. Okay, because I remove this term here from the integral and I obtain it, and you have integral of u prime v, that is minus the integral of u v prime, that is exactly the expression you obtain here, plus an extra term that is in my situation 0. Okay, and at the end, I have expressed my delta here. You see that you have delta without any derivative, And if I transform, so here at the beginning, I have transformed my expectation into an integral. Here I have my integral and I transform it into an expectation exactly this way, because here you integrate with respect to the density of n01. And so you obtain here, okay, my n01 here, or the square root of capital T minus Ty, will be exactly the Brownian motion at the point capital T minus T. Okay, so I obtain the delta in this expression without using derivatives here, and then my delta may be expressed using an expectation. An expectation here without any type of differentiation. Okay, so it's the sketch of the proof of the previous proposition that tell you here that the delta, and you can do the same for the gamma if you want as an exercise, the delta of a contingent claim of this form in the Black-Scholes model may be expressed as a kind of weighted expectation with what I have in the case of prices. It's of the same nature, but the only thing is changing is that here I add a random variable, that is this one in the case of a delta and this one in the case of a gamma. Okay, so I express, in fact, in this situation, my Greek no more as the derivative of an expectation, but as the expectation of my payoff multiplied by another random variable that I know in the case of the Black-Scholes model explicitly. Okay, so I have this. So have a look on this proof. Okay, so it's not that complicated to prove this result. I repeat, it is, okay, do it in 2 steps for regular and non-regular mapping. Step 1, regular, second step, non-regular, and I use the step 1 and I pass to the limit to obtain the step 2. In the step 1, when I am regular, I can invert the derivative and the integral here. Okay, so I obtain this expression. For this expression, I handle it a little in order to use integration by part, giving in mind that my variable of integration is y here. And here the variable of differentiation is x. So I change a little my expression in order to make appear y as a variable of differentiation here. It's exactly what I can do with this expression. And then classical integration by part in order to recover this expression of the delta as an expectation. Okay. So I have it. Okay. So the advantage of this approach or of this formula is that, okay, I have only one factor of approximation now because I have to approximate here to compute the delta and the gamma. I have just to approximate expectations. So I use just Monte Carlo methods, no more finite difference gain. Okay. And what is nice also is that the weight I obtain is independent of the particular form of my payoff, meaning that if I consider this family of contingent claim, the one that are pass independent, you see that the weights I obtain here and here are totally independent of F. I have something that is here independent of F. The green box is independent of F. That is the weights that are obtained. So it means that if you do this for a call option, for a digital option or something like this, you will use exactly the same methodology. Okay. So it doesn't depend on the payoff. So I have something here that is not more complicated to implement. Okay, that's what I do in the computation of prices when I don't have closed form expression. A question. So maybe concerning this question, I will drop it today. And I will do just a very small video of a quarter, okay, in order to solve it, okay? But I will drop it for the moment, and I will just show you to end this session. I will just show you, okay, numerical example of what I have done. Okay, so just drop this question and the two next slides for the moment. I will just record a very short video on this topic, maybe today in the afternoon or tomorrow, I would see. Okay. But now to conclude this session, okay, I want to see what we have done, okay, on numerical example. Okay. So what I have represented here. Okay. So what I do in this slide here. Okay. So I consider a call option. I am in the situation where here my F, my contingent claim takes this form, okay, where my F of small x here is just x minus k plus. Okay, I obtain this. And I am interested in delta t of x, that is the derivative of the price function with respect to x. Okay, so it's what I want to approximate here. And I am in the framework of the Black-Scholes model with these parameters. The initial value is 100, the strike is 100, the volatility is 15%, the risk-free rate is 5%, maturity 1 year, and I am interested in delta of 0. Okay, here, delta of 0. Okay, what is nice is that for the Black-Scholes model, I can compute this delta 0. It's exactly something that I have already show you. I have this board here. Delta 0 is equal to this one in the case of a call. So I can compute it explicitly. Let's do this. I compute it explicitly, and you obtain what I call the theoretical value from, okay, the tables of Greeks in Black-Scholes. You can compute it. You don't need approximations, okay, because you have a closed form expression. But what we are going to do here is to see what happens if I approximate this quantity that I know with the true previously mentioned approaches. So the one, okay, that use, okay, the one that use finite difference plus Monte Carlo methods, and the one that use, let's say, the weights. And by the weights, okay, it's the one that I have called here for mal for Malliavin. It's the one concerning the weights. And what I mean by the weights, it's just, okay, what I have obtained in these slides using, okay, this expression. It's what I obtained in the slide 66. Okay. So if I do the job here, okay, so I obtain the approximation in blue, the approximation that I obtain using the slide 66 in the case of the delta. So I have a single Monte Carlo approximation, okay, and I represent, okay, the approximation I obtain, it's the blue line here, depending on the number of, okay, of the size of my sample. And here I start from, let's say 1, and I go to, so 10,000, okay, 10,000, a sample of size 10,000, meaning that I generate 10,000 independent Gaussian in order to obtain the things here. And you obtain, okay, from the slide 66, the blue line, okay, for the approximation I do using the weight methodology, what I call the Malliavin methodology, with respect to what we are going to do from the next course. Second thing, use the naive approach, that is to use finite difference plus Monte Carlo methods. That is, I approximate the derivative by the finite difference scheme, and then I compute each term of the finite difference scheme using Monte Carlo methods. So it's what I have in pink here, okay? And what I can see on this picture here is that, in fact, the pink seems to be better than the blue. That is, finite difference plus Monte Carlo here give rise to an approximation that seems to be closer than the theoretical value than what I obtain if I use a single Monte Carlo methods, okay, obtained from the slide 66. So it means that all I have said before seems to be a little bit disappointing concerning this numerical result here, because the naive approach in these situations seems to be a little bit better than the one using the weight. Okay, why not? Let's continue. Concerning the gamma, so here it's not the delta that I am interested in, okay, but exactly in the previous situation, I am interested in the gamma, that is the second derivative, and what I see here, so in blue, the methodology with the weights obtained from the result obtained in the slide 66, and in pink, the naive approach, that is the one, okay, when you use the finite difference scheme and the Monte Carlo approximation, and in red, you have the true value, that is the value that you obtain from the closed form expression in the case of the Black-Scholes model for a call option. And here I see that, well, once again, so I can't even conclude in this situation. So the pink, that is the naive approach, seems to be a little bit better, but it is, if I can say, not that clear, okay? So the blue and the pink are not that different, okay, or less different than what we can have in the previous slide. Okay, so for the gamma, the pink seems again to be the best, but the difference between blue and pinks don't seem to be very big in this equation. So here it's what I can see on pictures, okay? So here you have the same thing, not for the call, but for the put, the delta of a put at time t equal to 0. And once again, you see here that the pink, that is finite difference plus Monte Carlo, seems to be a little bit better than the blue, that is the one using the result of the slide 66. Okay. And for the gamma, once again, a little bit more complicated in the case of the gamma of a put to distinguish between the two approaches. But once again, here, in the case of a put, my idea to use a weight in order to overcome the problem of using two sources of approximation doesn't seem to be very pertinent in the situation of the computation of the delta and the gamma of a call or a put option. So if I want to quantify a little bit the things, okay, because the pictures are nice, okay, but if I want to quantify, okay, the difference between the things. So you have the finite difference scheme and the integration by part, okay, that I use with the result of the slide 66. If I want to quantify if one is better than the other, okay, but keep in mind that the error I do when I use Monte Carlo methods, okay, are errors that are represented by the size of confidence intervals, Okay, so errors are driven by the size of the confidence interval, that is driven by the empirical variance. Okay, by the empirical variance. So it's exactly what I do here. Okay, so keep in mind that size of confidence interval at a level of 95% here is something of the form, okay, 1.96, okay, sigma over times this one over the square root of n, the number of simulations, okay? So the parameter for a fixed capital N and a fixed confidence level that drive, okay, so it's sigma, that is the empirical standard deviation. It is just the square root of the empirical variance, the corrected empirical variance as explained in the previous session. Empirical standard deviation. So here, what I represent by, and what I call by the ratio of variances, okay, is the variance of the Monte Carlo estimator for the finite difference. Okay, so it's something that is the variance of Monte Carlo estimator for finite difference over the variance of the Monte Carlo estimator from the slide 66. Okay. And I see that the variance, and so here the standard deviation, and so the variance, okay, is something that allow me to quantify the size of my confidence interval. So if I do this ratio, if I have a ratio that is greater than 1, it means that the variance of the Monte Carlo estimator for the finite difference is greater than the variance of what I obtain with the slide 66, and so that my methodology with the slide 66 is better, okay, than what I obtained for the finite difference. But in the case where the ratio is less than 1, it's the finite difference methodology that is better, okay? And I see that here, in almost all cases, except for this one where I am, let's say, near than 1, in this situation, as I have observed in the pictures, the ratio of the variance is here really strictly greater than 1 in these 3 cases, saying that the naive methodology using finite difference scale give me better result in terms of confidence interval than the one I can obtain using the formula proposed in the slide 66. The only situation where I have to discuss it a little more, okay, is in this situation where slide 66 give me, okay, a tool that seems to be a little bit better in situation, okay? But what I can see also in this situation here, I can also see that what I obtain in the case of the delta is a priori a little bit better than what I obtain in the case of the delta, okay? And what I obtain for put is better than what I obtain for call option, okay? So what can I say here is that, okay, a priori at this stage, that the finite this difference scheme using with Monte Carlo approximation give in the situation of put and call good results. In the case where I consider the put and the call, okay, I obtain results that are a little bit less worse, let's say, for my weight approach with respect to the finite difference, okay? But something that is not that significant, okay? So at this stage, I am a little bit disappointed because but the naive approach is better. Okay, so let's continue. Now, instead of considering a put or a call, we are going to consider a digital option, something of this form, something that pays 1 if you are greater than K mean and 0 otherwise. So what is easy to see is that in the case of the Black-Scholes model, okay, it's very easy to compute the price and the Greeks at time t equal to 0 or even at any time in this situation. And I have, okay, this closed form expression for the price, the delta, and the gamma at time t equals 0 for this payoff, okay? What I obtain from a numerical point of view? I obtain that, okay, in the case of the delta, once again, okay, or here it's a little bit different because what I obtain in the case of the delta of such an option. Here I see that if I want to compare the blue, that is the approach with the weights, and the pink, that is the naive approach, finite difference plus Monte Carlo, but it's that complicated to compare them here. Sometimes the blue is better, then the other one becomes better. Okay, so I am not able to distinguish here. Contrary to what happened in the case of the delta of a call and a put, where clearly the finite difference scheme was better. Let's see what happened for the gamma of such an option. And here it starts to be interesting now. You have in blue the approximation you do using the result of slide 66, and in pink the naive approach. And here you start to see that the blue seems to be better and better than the pink one. Something that I can quantify, okay, writing the ratio of the variances. In the case of the delta, the integration by part methodology, okay, has a variance that is 5 times smaller than the one obtained by the finite difference scheme, okay, and a number that is really impressive is this one. That is the ratio of the variances in the case of a gamma, okay, is equal to this one, okay, let's say around 2000, okay, 2000. So just have a look on what is the meaning of this and of this order of magnitude here, okay? So the ratio of the variances is equal to this term. So it means that the ratio of standard deviation is the square root of this one, let's say. I don't know what it is, but let's say it is, I don't know, something like this, 45. Okay. This, yes, looks like this. Well, something like this, let's say, more or less. So I have a ratio of standard deviation that is this one. If I am in the finite difference, okay, approximation, the size of the confidence interval is, okay, 2 times 1.96 over the square root of n, sigma 1, okay, where here you have the standard deviation related to the finite difference. In the case of the integration by part, the size of the 95% confidence interval is given this way, sigma 2. And suppose that you use the sample of size n1 here and a sample of size n2 here. And I know that sigma 1 over sigma 2, in the case of the gamma here, is more or less equal to 45. Okay, I have this. And what is the meaning of this? It means that if I want to obtain the same size for the two confidence interval in this situation, okay, if I want to obtain the same size for the two confidence interval, then I have to consider in the finite difference scheme, okay, an ensemble of size that is the size of the one I use for the integration by part methodology multiplied by 45. So that is that to obtain the same degree of precision with one method and the other, I have to use a sample size that is multiplied by this. Something that is really huge, huh? Because in general, okay, if I use 1 million simulation to obtain this, okay, or to obtain a precision with the integration by part methodology, I will need to use a sample of size 45 millions. And if I do this for a huge number of products, okay, at the end you have a difference of computation times that is really huge, in fact, really huge, okay? So you see that here in this situation, the idea of suppressing the derivative by introducing a weight allow you, in the case of this digital option, to improve greatly the size of the confidence interval I obtain for a fixed level and a fixed number of simulation. So let's continue with the last example. So what I have done here, so excuse me, here I am in the situation where I will consider another kind of option that is what we call the corridor. So in fact, it's the difference between two digital options considered in the previous way. So it's something that will pay you 1 if you are between K-min and K-max and 0 otherwise. Okay, it's a corridor option. And in fact, we have also closed form expression in this situation because a corridor is just the difference between two digitals. And in the case of digitals, I have the closed form expression I have previously mentioned. Okay, so if I do this here, I see that for the delta, once again, I see that the blue is better than the pink. That is, the weighting method is better than the naive one. And for the gamma, I obtain something like this, where here, okay, you don't see the blue anymore with respect to the pink. And if I want to quantify a little, okay, but you have, even here in the case of the delta, you have results that start to be really interesting. And for the gamma, okay, you have the ratio of variances that is really huge, okay? The variance relative to the finite difference game is, okay, let's say 6,000 times greater than the one obtained by the weighting method, okay? So something that will impact a lot the size of confidence interval. So if I want to summarize what I have obtained here in the numerical things, I see that for the call and the put, not that interesting. For the digital, it starts to be. For the corridor, okay, it confirms to be. And what is the difference between these three payoffs? Okay, the three payoffs are just different in the following way. In the case of the put or call, you have a continuous payoff function. Okay, and the classical things, something like this. In the case of the call, okay, and in the case of the put, okay, so excuse me. So you have the payoff of a put here, okay, so it's the payoff of the call here. That is just representing x minus k plus. And if I represent what happened for the put here, it's what I have for the put. Okay, so if x is greater than k, I obtain something that is so something that is 0. I don't have negative values here. It's stupid what I have done here. It's something like this. Okay, and I obtain something like this for the put. Okay, so you have continuous payoff. If I consider the digital, that is the indicator function of x greater than k, I have 1 point of discontinuity. Discontinuity. If I consider the corridor option, I have 2 points of discontinuity. So I can deduce that the more irregular is the payoff, the more efficient is the integration by part methodology. If I increase the number of discontinuity in my payoff function, I see that I am better and better. In fact, using the weighting method with respect to the finite difference one. Okay. And I see also that the method is better for the gamma than for the delta. Okay. And I see that, in fact, the way it improves the things come from, in fact, a reduction of the variance, because the variance, so in the good situation, the variance I obtain in the case of the result obtained from the slide 66, the weighting, let's say, okay, the one coming from the integration by part, that I will call in few sessions the Malliavin method, decrease the variance of Monte Carlo estimators a lot. Okay, so I have this, and I have also observed that the integration by part perform better for a put than for a call. And why it's better perform for a put and not for a call? Okay, but because you have this here. Because here you have something that is bounded, the payoff of a put is bounded, and here the payoff of the call is not bounded. So it means that since we have obtained weights that are, okay, polynomial in the Brownian motion, in fact, here, but the weights is potentially big here, while here it will be bounded in all situations. Okay, so that's why I obtained this. Okay, so I have this. And concluding remarks. Okay, so the concluding remarks we are going to do is that, well, okay, I have done the job, okay, for something of this form in this course today, but I can do exactly the same for payoff of this form. Okay, if I am not just a function of the final value of the risky asset, but a function of a finite number of values of the risky asset, I obtain this kind of formula for the delta that you can try to do at home, okay, by yourself. And it means that, okay, in the case of the Black-Scholes model, okay, I can use this integration by part methodology also for, let's say, a discrete look back or ASEAN option that are discrete option on means or discrete option on maximum, because I have an easy extension of what I have done in the case of the slide 66 to payoff of this form. Okay, not necessary to be a function of the final value, but just function of a finite number of values. And the natural question that appears to conclude this introduction is, in the case of the Black-Scholes model, what happened for other models, and also what happened for other models than the Black-Scholes model. Okay, so, and you will see that in what we are going to do, okay, it will even be interesting in the case of the Black-Scholes model, because we are going to consider this type of option in the case of the Black-Scholes model when I don't have closed form expression and where I can't use integration by part as proposed in the slide 66. So in the Black-Scholes model, we are going to be interested in what we call ASEAN option that we are not able to do even with what I have said today. And we are also going to see that, okay, but I am able to extend the integration by part argument used in Black-Scholes to more general models. And if I want to do this, I need, so to extend this integration by part argument, and the integration by part argument I have used in this proof here. Where is it? Yeah. This one, that is a classical integration by part argument that it is possible to do because in the Black-Scholes model, I know everything. In fact, okay, I have the density of the risky asset, okay, so I can use explicitly all the things. If I use a more general model where I can't use this kind of explicit computation, how to extend my argument of integration by part, this is the aim of one of the aim of what we are going to call Malliavin calculus. The Malliavin calculus will allow us to extend the integration by part argument obtained easily in the case of the Black-Scholes model to more general financial models. So the program for the next classes will be, for the 3, let's say, next classes, I will do maths and only maths, nothing to do with finance, okay? I will introduce the Malliavin calculus and will study the related operators, okay? And then at the end, I will apply the mathematical tools we are going to see together to how to extend this integration by part argument, okay, that I have used in the Black-Scholes model to improve the quality of the approximation of Greeks by Monte Carlo methods, okay? So I don't forget that I have to record a small video concerning, okay, if I have several weights, how to choose them in an optimal way, okay, I will do it, okay, maybe this afternoon or tomorrow. But this introduction is closed, okay, and see you next session to start the mathematical part of the course. So see you, bye-bye.